Yeah, this is こいや2つ同時に使わない方がいいっていう感じですね。Yeah. Okay. Yeah. So hi, I'm Ryo Kazuwara, and I'll be talking about end-to-end encryption, and it saves lives. So you can start saving lives with Ruby too. So slides are available at this URL and for this QR code. And if yeah, in the morning session, like people said, like Hasumi said, like nobody looks at speaker deck, but like there's a lot of text and lots of diagrams. So and there's total of 94 slides, I believe. So. Please have it on your phone or on your computer to look to watch. I'll be starting in about 20 seconds. This is a slightly updated version from the Ruby Kaigi talk, and like I've added lot more explanations because the Ruby Kaigi version was very rushed. And so let's start. Hi. I am from Matsuyama, and I flew from Matsuyama MYJ to Songshan TSA, and to find this advertisement of Dogo Onsen, which is in Matsuyama, in Taipei. This is in Shinbeito, and that was where I stayed yesterday. And so I do a lot of stuff. If anything catches your interest, let's talk. And I do more stuff that is more relevant to this talk. I am a freelance web developer focused on digital identity and security, and I've been working on writing, editing, and implementing standards such as HTTPS and local network, Web of Things working group in the W3C, and OAuth and messaging layer security working groups of the IETF. And I've worked as an officer of Internet Society Japan chapter until 2023. And there's a usual disclaimer about talking about cryptography. Cryptographic API is very easy to misuse, and operational security is also difficult because even if the protocol is secure, if you misuse it, there will be security breaches. You've seen it in the news. And I've done my research about this topic, but I don't consider myself a cryptography expert, which means I am not DJB. And also, I don't have a PhD or master's degree in this field, so yeah. If you're not sure, please have your system audited by a security expert before going to production. And speaking about production readiness, the MLS implementation I'm talking about today is not production ready at all. It's very much a prototype, and it passes most test vectors but lacks validation on error cases. And client implementation is underway. I was trying to get this ready for this talk, but yeah, I'll hopefully release 1.0 by the next IETF, which is in November. And yeah, first I'll talk about the motivation getting into this talk. So I happen to be known as the SMTP or Yamero guy, which means stop using SMTP, more like SMTP is dead. Because I have two problems with SMTP. One, that it lacks strong identity. You are able to spoof identity easily on SMTP, and also SMTP lacks end-to-end encryption, which means the people who run the services cannot read your messages if you have end-to-end encryption. Line, Facebook Messenger, Signal, WhatsApp, those apps you use for messaging, they all have their own version of end-to-end encryption. And to talk about why it's important, we have to mention some international affairs, so bear with me for a while. So end-to-end encryption is more important than ever because there is increasing tension in international affairs, and also powerful people, even in democratic countries, want to control the internet and your communications. So end-to-end encryption provides a safe method to communicate under oppression or in war zones, which means it saves lives. But you might have heard that end-to-end encryption also helps criminals. That's the reasoning that authorities target end-to-end encryption by. Like, But even if you ban end-to-end encryption, criminals will use it anyways because they are bad people. Banning end-to-end encryption disproportionately harms vulnerable people. And this is an example that the Internet Society published a blog post titled "Encryption is a preventative tool that protects children," which explains how encryption is beneficial for children, who can be considered vulnerable on the internet otherwise. You might have heard of HTTPS or TLS also helps criminals, but if you ban HTTPS, you are not secure. Like, everyone is not secure on the internet. So let's go back to talking tech. Messaging layer security is an interoperable way of doing end-to-end encryption, and specifically, it provides key exchange. And there are two major documents in MLS, which is one is the protocol RFC 9420 and the architecture document RFC 9750, which got an RFC number very recently. Today's topic is the implementation of the protocol, and we kind of have our RFC 9420 on Ruby, and so you can say that MLS brings interoperability in secure messaging. We could say that SMTP is MLS is essentially SMTP o yamero. And I try to call my gem MLS, but MLS gem already exists for a defunct website. The name of the gem is called Mellows, which is taken from a novel that's in most Japanese middle school textbooks. So, let's talk about the protocol. This part will be the major update from the RubyKaigi talk. So, you might have heard of symmetric and asymmetric crypto. And symmetric crypto is the one that uses the same key for both encryption and decryption. And asymmetric crypto is also known as public key cryptography. It works like this. Alice keeps a pair of keys, which is a public key and a private key, and she publishes the public key on the internet. Then Bob encrypts the plain text, which he wants to send to Alice, using Alice's public key. Then Alice can decrypt the ciphertext, the encrypted text, with her private key. And to do this encrypt with publicly, decrypt with private key thing, you might have heard this in TLS, but there's a formalized way to do this called HPKE. You might have heard this from before, because I've talked about HPKE in Ruby at RubyConf Taiwan the last time, 2023. So this is a combination of key encapsulation mechanism, which is the asymmetric crypto, and a key derivation function, which is essentially a hash, and authenticated encryption with associated data, AEAD, which is a symmetric crypto. And this is already available in Ruby as an HPKE gem. So there are two major characteristics you want out of secure messaging. One is forward secrecy, which means messages sent at a certain point in time are secure in the face of later compromise of a group member, which means it is secure against the harvest lots of ciphertext now, then decrypt later with a higher computational power. And the other is the post-compromise security, which means messages are secure even if a group member is compromised at some point in the past. So each member updates their key frequently so that the group secrets are not always encrypted with the same private key all the time. So forward secrecy provides security before the compromise. Then the post-compromise security provides security after the fact that compromise took place. To achieve this in two-person, it is kind of easy. You first get both two parties start with the same common secret, chain key 0. And to send message 1, you use the chain key 0 and you take the HMAC SHA-256 of that, and the next chain key will be produced using the HMAC SHA-256 of using a different 0x01 and 0x02, so the message key and chain key won't be equal. But doing this with 3+ persons is difficult, which means it is very difficult to agree on the same secret for 3+ persons. If you want to extend the two-person method for everyone, the number of edges in an n-node complete graph is O(n) squared, which is problematic. So MLS uses your favorite data structure that turns O(n) into O log n, which is trees. To do trees with arrays, MLS uses a complete balanced tree, so this can be described as a flat array like this. So the tree on the right will be written as 0, 0, 1, 2, 3, 4, up to 9. The 10 is missing, so it's a nil. Then the next is an 11. Then the rest is nil. So the leaf nodes are always even numbered, 0, 2, 4, 6, 8, and the parent nodes, which have a child, will be always odd indexed. And we define operations such as left of an index, right of an index, based on the characteristics. And these algorithms are all defined in the appendix of the RFC 9420, and it comes with the serialization and deserialization format, so it's pretty convenient. So to agree upon a common secret, there are 3 parts to MLS, and this is a diagram from the RFC, but it's kind of confusing, to be honest, because it hides the fact that there are actually 3 parts to it. So the tree, there are 2 trees. One's called the ratchet tree on the left, and one's called the secret tree on the right. And users in the group will be assigned a leaf in the both the ratchet tree and the secret tree. So you will be if the first user will be index 0 on both trees. Second user will be index 2, index 4, and so on. So what you want to do is you want to agree with other users in the group upon a common secret, which is called the epoch secret of n, which is the n is the epoch number or generation number. So for the first part is secret tree. If you have a common secret, which is the epoch secret, you can the group can derive the same symmetric keys for encrypting messages created using the secret tree. To create the secret, you go down from the root and produce secrets from in the tree, left, right. You take the hash of the common secret, then create secrets down to the leaf. Then the actual ratcheting part looks like this, which looks very daunting, but it essentially boils down to this. You derive the key and the nonce from the same ratchet secret of the node. Then the next ratchet secret will be produced from the tree's ratchet secret of the last generation, or the last message. Then compare this with the two-party method of hash ratcheting. It looks pretty similar. And the next part is called the key schedule. With the last epoch secret of the last generation and the common commit secret, the group can agree upon the next epoch secret. Commit secret and epoch secret n is used to create the epoch secret n+1. So if we assume we can get the commit secret for every member, we can assume that the group's secret state is consistent among all the group members. This part is nothing much different. It's a hash of these 2 strings connected together. It's essentially like that. But the hardest part is called the tree KM, which is agreeing upon the commit secret. So we said that users are assigned a leaf node, and users have their each leaf key pair, the public and private key pair. So, when a user wants to update the group secret, the user will first create an update path. So, how the update path is created is the user generates a random path secret at their leaf. And then the parent's path secret, the parent of 0 is 1, so 1's path secret is calculated using the child's path secret 0, which means they take a hash of that. Then calculate that up to the root 137. Then the commit secret is calculated from the root's path secret, the root 7's path secret. So it looks like this. Path secret 0 is a random value. Path secret 1 is the hash of the path secret. Path secret 0. Path secret 3 is created using path secret 1. Then the commit secret of the entire tree is created using the root's path secret, which is path secret 7. So when the user 0 creates its update path, which is a yellow, we want to find the copath nodes, which are described in green, along the update path. So copath node of 0 is 2, 1 is 5, and 3 is 7. then if all parent nodes in the tree are populated like this, we will encrypt the path secret of the to the key of its copath nodes. Let's say one's path secret is encrypted using 2. 3 will be encrypted using 5. 7 will be encrypted using 11. And the public keys for parent nodes are with the keys to encrypt are derived from path secrets. So we can see that this is possible in a 2-leaf tree. Let's say 0 creates an update path, node 1 has a path secret, and it is used to create the commit secret. And the path secret of 1 is encrypted to user 2's public key. And node 2 knows the private key to node 2, which means so user at node 2 can decrypt 1's path secret, so user 2 can create the commit secret, and 0 and 2 knows the common commit secret. But what happens if there are blanks in the tree? And there will be blanks in the tree. So what we'll do is we calculate the resolution of the copath node to figure out which node keys are available. We'll describe that later. And when we'll encrypt the path secret of update path node to each key of that resolution. So to calculate the resolution, the resolution of the node indicated on the right is will become 3, 2 in that order. The indicated node in purple has unmerged leaves, which will come out later. So its resolution is itself index 3, and the list of unmerged leaves, which is 2. In this case, the resolution of the node at the root will become 3, 2, 9, 14 in that order. So the resolution for the root was calculated using the resolution from the left, which is 3, 2. Then the right has a blank, so it goes down. And the left is 9. You go down, and the resolution is 14 at the end. So resolution is used to figure out the set of keys that are necessary to encrypt to every node under that node, which means to encrypt is user 0, 2, 6, 8, 10, and 14 on that tree, you need to have the keys of 3, 2, 9, and 14. So actually what you do is you calculate the path secrets for each node on update path 1, 3, and 7, then encrypt the path secrets to each key on the resolution of the copath node, which is in this case 2, 5, 11. And if there are blanks, you figure out like I described before. So encrypting the commit secret itself and sending to everyone, like you can encrypt the commit secret to 2, 4, 6, 8, 10, 12, 14's public keys and send it to everyone. But that is ON, where N is number of members. But encrypting the commit secret along the copath reduces the number of encryptions needed to O log N, where in this case it's 2, 5, and 11. So it significantly reduces the number of encryptions needed. So to summarize this, the secret tree, the part on the right, gives you the per message sender keys based on the epoch secret, and the key schedule gives you the next epoch secret based on the current epoch secret and commit secret. Then to agree upon the commit secret, you use tree KEM, and you get the commit secret for each member. To send to encrypt actual messages, you will create a framed content. You sign it with and get an authenticated content. Then you wrap it inside a private message, which will take the authenticated content and the secret tree and encrypt it to the using this sender key. And to create a group and to use the group is updated through messages called proposals and commits. Proposals will add and remove users from the group, notifies an update of a user's leaf key, and injects pre-shared keys. And the commits will fix those informations and advances the group epoch into the next generation. And the updated path used created before are conveyed in the commit message. And So group, it will be created by adding a user's leaf node into a zero node group. Then starts with a random epoch secret like this. This is from a work in progress version of the MLS implementation. So it will create the first ratchet tree with a single node. The leaf index of your user will be 0. Then you start with a random epoch secret. Then the users who want to join to that group will publish their identity using a key package, which is you will publish your public key, and then they will receive a welcome message that has a group state encrypted to that public key. So when a user A creates the initial group, and to add user B, A sends an add proposal, adding B, then commits that add proposal. Then the A will send a welcome message to introduce B into the group, which has the encrypted group state of the group. Then you will do the same for adding C. What happens to the tree is when you add a user, you add a leaf node from the key package to the leftmost empty node. Let's say in this case 10 is empty, so 10. You will add the leaf node to 10. Then you will add the leaf index of the 10 to the intermediate node's unmerged list. So 9, 11, and 7 will have 10 as unmerged leaves. To update the key for, let's say, user B, user B will send an update proposal notifying the group of its keys update. Then let's say another user commits that update to fix that to the group state. So what happens is when you will replace the leaf node with an updated leaf node, then you will blank all the nodes on its direct path up to the root. Let's say 4 updates its keys, and 5, 3, and 7 will be blanked. Then to remove a user, let's say Z sends a remove commit to remove B, and commits it, and all the group members will be notified of the removal of B, but B cannot decrypt the path secret of the new commits update path, because B will not the group's new state will not be encrypted to B's public key, so B will not know the next epoch secret, so B cannot advance to the next generation. So what happens is when removing, you blank the specified node, let's say number 8, then blank all the nodes, let's say 9, 11, and 7. But in this case, the right half of the tree is fully empty, so the next root will be 3, and the tree will be 0 to 6. So the intermediate parent nodes will be filled during the processing of a commit, and when processing a commit, the update path inside the commit will be merged into the ratchet tree, and the parent nodes are created based on the update path. So there are lots of stuff that I'm omitting here, like injection of pre-shared keys and transcript hashes and signing and verification of messages. But it's already getting too long for explaining this protocol. So I might do it in a different talk or a different blog post later. So I'll explain about like ongoing and future work about this implementation and encryption in itself, like cryptography in Ruby. The current implementation state is like it passes most test vectors, and I've added some updates to the implementation, like passing messages, parsing messages now uses a string IO instead of using 2 strings, and move the group all the group state into a group object, but it needs a user-friendly client API to use it, because you don't want to like create a frame content, authenticated content, wrap it in an app message. That is too difficult for users to use. So it needs user-friendly API, and I want to test it against other languages implementations. It kind of looks like this right now. You will create a client, you create a key package of that client, and you create a leaf node, and you create a group with that leaf node, and you will add user two's group leaf node with an add proposal. Then you will commit it, and group two will receive a welcome. And it's I'm currently working on this. So there's like some stuff that you can contribute to. Like there is very heavy refactoring needed, and I'm currently wrapping raw values that are in the test suite into the classes. One is a group that's being worked on, and now but the ratchet tree is now represented as raw array, like I described. So that needs some heavy refactoring, and also you can help with interoperability testing, like learning other implementations and create test scenarios. And there's already an automated interop suite in other languages implementation that uses gRPC. So adding that to Ruby will be very helpful. So there are some other works on Ruby's crypto ecosystem, like HBK using OpenSSL's API. I've talked about this in the last RubyConf Taiwan, and I'm thinking it kind of might not be a good idea, because the protocols needs the whole cipher suite, not only the functions. And you want to access constants such as hash and key lengths, like this. So to get the sender data key and data nonce, you need to know how long the hash length is, how long the key length and the nonce length, which you cannot directly access through OpenSSL's API. And this might not be a missing feature from OpenSSL Gem, but I found it difficult to have a consistent API through the normal ECs and Edwards curves such as X25519 and X448. Like this is if you want to check if the private key and the public key corresponds, it actually makes a pair. There's a different API for Edwards curve and a normal EC, and also getting the key pair as a uncompressed point representation form, which is required in the RFC. You have to use a different API for Edwards curve and the EC. And also, OpenSSL 3.350 ships with the post-quantum cryptography. And there's an internet draft that tries to add MLChem into MLS, so that also might be another place to work on. And you might be thinking MLS is end-to-end encryption, so it's a client-side thing. It's a Ruby is a server-side language. Ruby is Rails, right? No. Ruby's not just Rails. We have Ruby WASM. So to work with Ruby WASM, browser uses Web Crypto API. Actually, Ruby WASM has OpenSSL compiled with WASM, but it's more performant to do through Web Crypto API. So I want to have a unified API wrapper that works on desktop, browser, and embedded embedded TLS, which is already supported in PicoRuby. So I have a very quick example of calling Web Crypto API's random number generator like this, but I want to have a more cleaner API, so I'm currently working on that. So to end this talk, let's answer the question in the description of the talk. Why do you need end-to-end encryption in Ruby? Because, one, Ruby needs to stay relevant. I've talked about the same thing in the last RubyConf Taiwan talk. If you don't have modern cryptography in Ruby, people would just use Python, Go, Rust, whatever the cool kids use these days. But Python doesn't have an MLS implementation, so it's a win for Ruby. And two, Ruby needs freedom on the internet, and the free internet needs Ruby. And so the major takeaways from this talk, we have interoperable ways of doing end-to-end encryption. And we kind of have this in Ruby too. And for your daily uses, please use secure messaging in your daily life. And I would like to give some shout outs to the messaging layer security working group. Congratulations for them to getting their MLS architecture document as an RFC, and also their shout outs to the protocol implementators in Ruby. The list is growing, and also thanks to the RubyConf Taiwan organizers for having me here. So if you have questions, comments, You can find me on Twitter at S01 or Fediverse S01 at ruby.social, or find me in the venue and at DrinkUps. I was planning to be at the official code party, but I'm kind of feeling not so good today, so I am not I will not be at the code party today. Sorry, and that's the end of my talk. Thank you very much.